Hey guys, in this video we are going to be simulating a flow through an elbow. So the geometry is going to look something like this, and if I cut the geometry you can see that there's also a throttle valve. So we are going to be running two sets of simulations. In the first simulation we are going to be doing a steady state analysis. So in the steady state simulation the throttle valve is going to be fixed and we are going to see how the flow takes place around it. And for the transient analysis, we are going to be rotating the throttle valve to see how it affects the flow downstream. Okay, so I've already created this geometry and I've also exported the required STL file. And let's open up Converge Studio. And what I'm going to do is I'm going to just drag and drop my model. So I've also shared this geometry with you. So you're going to be watching this video and you are going to be setting up the same problem. Now the key difference is the way the geometry is oriented in my case is completely different from the way it's oriented in your case. So whenever I type in some numbers for translating or rotating the model, those numbers do not apply for you. So if you just copy it blindly, your simulation is going to crash. So the main reason why I'm doing this is for you to understand the concept, and then you need to apply those concepts for the same problem, but the geometry being located in a different place. So we have an elbow here and you can see that the pipe has some thickness to it. And as always, the first thing we need to do is boundary flagging. Before we do that, let me run the diagnosis to see if there are any problems, and looks like the geometry is okay. So what I want to do now is go to boundary, find /clean, and I'm going to create boundary fences automatically. You can see that it has flagged the boundary fences correctly. And in this case, there is a thickness to the elbow which I really don't care about. If I'm doing a conjugate heat transfer simulation, then that thickness is of interest. So in this case I want to delete it, and there are several ways I can delete the triangle. I have angle selection by default, so I can just select the outer pipe, make sure that no internal parts are being selected, and if hotkey is enabled, if I hit D, the geometry gets deleted. Similarly, I can delete this section right here and this section right here. Okay, so if you have to undo, if you accidentally delete something, use Ctrl Z to bring those triangles back. Alternatively, you can also go to repair, delete, and you can select the triangles. You can see that the selection appears. You can do this first to basically gain some confidence in those operations, and then once you're comfortable, you can switch to the hotkeys. I select the triangles again, delete it. Alright, so now I have my geometry. You can see that I have yellow edges here. These are open edges. So if I run the diagnosis right now, you can see that there are 211 open edges. The problem is because they're open and they need to be closed. So how can I close this? Well, I can use the patch tool. So I can go to repair, patch, and you can see that automatically I'm in edge selection mode with open edge selected, and I can just select the inlet face, the inlet edge. Actually that's the outlet edge and this is the inlet edge. So the next thing I need to do is create separate boundaries. So I'm going to go to boundary, flag. I already have one boundary here. I need 3 more boundaries. So let's create multiple boundaries and let's add 3 boundaries. So my outer pipe is going to be boundary number 1. So I can go to view options and hide that boundary. And what I can do is for inlet, I can just say that this is my inlet, and I can say that this is my outlet. Now if I hide my inlet and outlet boundaries, you'll be able to see the throttle body. One thing you can do is if you go to diagnosis and if you click on clear, the highlight is going to go away. Sometimes it comes in your way and you don't want it, so you can just clear it. So here I need to select the throttle. How do I do that? Well, it's inside, so there are a couple of options. So first, I can just put the geometry in a straight view, use the box select mode, and then maybe just select something like this and right click, and I can just hide selection. So this way I can see the throttle inside. Alright, so Converge Studio does not have a very nice clip feature like SolidWorks. It does have one, but it's not as good as SolidWorks. So here I have the geometry. So what I can do is I need to select this entire throttle plate. Now you can see that the throttle plate is completely closed. There are no holes or errors in the geometry, and it's not connected to the pipe anywhere, right? So in a real life geometry, there's a shaft that goes through the pipe, right? And you have gaskets or O-rings to prevent leakage. So in this case, we don't have any of it, and hence the throttle plate is a separate surface. It's a closed surface. So which means I can select a boundary and go to cursor pick and then use the surface method to just click on the throttle. So this way I've added throttle to a separate boundary. So with that, my boundary flagging procedure should be complete. I can enable the normals to make sure that the normals are all pointing towards the fluid domain. You can see that some of the normals are actually pointing outside. That is actually because these normals belong to the throttle and they are just coming out of the geometry. It's just a rendering issue. So what you can do is you can zoom in and then toggle that normal visibility, and that problem should go away. Okay, cool. So now if I go back to diagnosis, you can see that there are no errors. You can also run this additional check that all normals are pointing to the interior, and if that check passes, you are all good to go. So our boundary flagging is complete. The next thing we are going to be doing is the case setup. All right guys, so now that the flagging part is complete, we can set up the case. I'm going to go to the case setup and then click on begin case setup. In this case, we are interested in a non-reacting flow simulation. So non-reacting flow simulation is one where only the flow is simulated and no combustion or chemistry is simulated. Okay, so in this case, I'm going to go with general flow. So the next thing I want to do is click on materials and select predefined mixtures. So when it comes to computational fluid dynamics, you're solving a bunch of transport equations or PDEs that have physical properties of fluid involved. So with respect to thermodynamic properties, NASA has a neat polynomial format that can be used to calculate your specific heats, entropy and enthalpy. And similarly, other properties have also been documented either through experimental techniques or analytical techniques. So with respect to Converge, you will see that in your input files, you will have a file called therm.dat, which contains the thermodynamic data. And then in addition to that, you will have a file called gas.dat. As we learn more about Converge and CFD, we will try to understand these physical properties in more detail. So in this case, I'm going to be simulating only gas flow. All right. And for global transport properties, let's just click OK. The turbulent Prandtl number and Schmidt number, for now, we are just going to use the default values. I'll explain to you what those are in a later video. So now we are going to be setting up our simulation. So think about this. In this case, we are first going to do a steady state simulation because the valve is not going to be moving. All right. Our end goal is to get a final flow field, or it could be, pressure drop, or it could be a mass flow rate. That is the quantity of interest. So in this case, we can just set it to pressure based steady solver and let everything else stay the same. Okay, so Converge is going to load some default constants. That's fine. With respect to simulation parameters, I'm going to start at 0 and then I'm going to run this up to 15,000 cycles and let the initial time step be 1e minus 9, and I'm going to say that the minimum time step is also 1e minus 9. So far, we have done 3 simulations, right? And you will see that in all the simulations I start with 1e minus 9. Why is that? So Converge uses a dynamic time stepping algorithm. So at each and every time step, Converge is trying to see if the time step can be increased for the next coming time step. Okay, so if your initial conditions, boundary conditions and mesh are good, then the time step is going to increase automatically. All right, so don't worry about starting from a lower value. With respect to maximum time step, I typically give it as 1 second. Usually it never gets there. With respect to time step, it depends upon your CFL number. So CFL number determines the stability of your solution, and there are several types of CFL numbers. This convection based CFL number, diffusion based CFL number, and another CFL number based on the speed of sound. So we're just going to use the default values, and as part of your exercise, you will be trying out different values for CFL numbers, and you will be documenting your observation. So let me click OK here. Solver parameters, we're not going to change it. So let's just click OK. So now we are ready to set up our boundary conditions. So what I'm going to do is I'm going to treat this as my inlet and this is my outlet. Again, it's a made up geometry, so it really doesn't matter. So boundary 1, I'm going to say that it's a wall boundary, and it might actually be a good idea to go to view options and first give the boundaries some names. So let's just call this as elbow wall, hide this guy, and this is going to be my throttle, and this is my inlet boundary, and this is my outlet boundary. So let us say that the elbow wall is of type wall, and throttle, what I'm going to do is I'm going to say it's also of type wall. Now you will see that there is something called as law of wall boundary condition that gets applied. This is applicable whenever your flow regime is turbulent. At the inlet, we are going to specify total pressure. So the idea is we are going to specify a pressure drop. That's going to be my boundary conditions, and then we are going to see what's the mass flow rate through this particular elbow. And we are going to say that the inlet total pressure is 1.5 bar. So I can just use 1.5 E5, and then the fluid that's flowing in is air. And at outlet, we are going to specify a static pressure, 1 bar. Okay, so we still need to create a region. That is why we are getting this error. So we go to case setup and let's add a region. All right, so now that we have added a region, let's assign all of our boundaries into this particular region. Okay, and if I go to case setup, right click on boundary and validate, the error should go away. As far as the turbulence model is considered, we go with the standard RNG K epsilon. And for base grid, we use 4 mm base grid. That's going to be our starting. And we'll look at the results and we will fix things accordingly. So here you can see that the base grid size is very small. Oh, okay. All right, I know what the problem is. So, when I imported the geometry from SolidWorks, I forgot to scale the model. So in SolidWorks, the geometry was created in millimeters. And when we imported it to Converge, it thinks that this is in meters, which is bad. So I'm going to transform my geometry, transform scale. I'm going to apply a uniform scaling factor of 0.001. So now if I validate my base mesh, that seems okay. With respect to post-processing, I'm not going to add any new variables. So I think this is fine. So we are ready to export our simulation files. So I go to export input files, and let's save it in Converge runs. And I'm going to create a new folder called elbow flow. And then, let's create a subfolder for steady state simulation. And then we are going to dump all of our files over there. Okay, perfect. So now what we need to do is we need to go and run the case, post-process the results, look how the grid is, and then we are going to be talking about some grid refinement strategies. All right, so I'm going to open up Sigwin and then navigate to Converge runs, and we are going to go inside elbow flow, steady state. And what I want to do is, initially before running the job in parallel, I first want to make sure that the job actually runs. So to do that, just run it in serial and make sure that you're able to see the outputs. Okay, so looks like it's working, right? We are at cycle number 117, so which means everything is looking good. And with respect to cell count, you can just look at the cell count ranks.out file. So here we are saying that we have about 1000 cells, that is really small. So we know that we need to increase the number of cells. Okay, so here for each cycle of the steady state simulation, we are telling what the total number of cells is. And since this particular job is run on one processor, we just have one additional column. So Converge uses MPI programming to parallelize the solver. And in MPI terminology, rank refers to your processor. So if you have 3 processors, okay, then rank 0 basically refers to your first processor, rank 1 is going to refer to your second, and rank 2 is going to refer to your third processor. Since it's a serial run, it's just going to have one column. Now if we run the job on two processors, we are going to have another column called rank 1, and the sum of cells in rank 0 and rank 1 is going to be equal to the total number of cells, right? Which should make sense. So in this case, clearly the base mesh is really large, and that is why the total number of cells is less. So let's actually close this and go to output folder. You will see that you already have a single post file. Now we can use this post file to take a look at the initial mesh. So I'm going to go into 3D post processing. I'm going to call my case name as test, and let us navigate to the right folder, elbow flow, steady state, output. And I'm just going to click on all and convert. So you can see that I have the finished keyword, which means the process is done. So next, what I'm going to do is launch ParaView. So one thing that you should know is ParaView can also read data that has been written out in Insight format, which is very good because Insight is a commercial tool, whereas ParaView is open source. So now we need to navigate back to our folder where we ran the simulation, elbow flow, steady state, output, and we are going to open up this group file, which has an extension .vtm, and then just click apply. So you can see that you have the geometry. So in Converge Studio, right, we created boundaries, inlet, outlet, and so on. So the same thing can be seen here as well. So you need to go to view and then click on multi-block inspector. And then if you click on multi-block inspector, you will see all your boundaries. So your cell data refers to your mesh. Now if I hide the mesh, the geometry is going to look smooth. The reason why it kind of looks weird is because you are trying to show the mesh and also the surface information, basically your surface triangles, and that is why it looks a bit weird. So typically hide your cell data. And what we can do is for the elbow wall, I can just adjust the transparency a little bit. And if I just click on the test.vtm, things are going to be clear again. Okay, so that looks good. So now what I'm going to do is I'm going to create a clip plane. And if I go to properties, I want to cut the geometry very similar to the way we looked at it in SolidWorks so that we can see what's going on inside. So, I think if I use a Z normal, it's going to cut it in the right way. And, you can just put the geometry in different views to make sure that you're cutting it in the right location. By default, it uses the right plane. And if I click apply, I'm going to get a new part. You can see that a slice has been created, and we can display the mesh. And you can see that when I display the mesh, I get this triangulation. Now the reason why that happens is you can see that there is triangulate the slice option. So we just click on that and click apply, and that problem goes away. And we can also go back and hide our plane. We don't have to see it anymore. And if I put the geometry in this view, you can see that, my mesh size is really big. I need to increase the refinement. And here you can see that if I want the flow to go on top of the throttle plate and in the bottom right, I need at least a few cells. The meshing technique that Converge uses is called as a cut cell Cartesian method. So you can see that no matter how big your base grid is, we actually cut the surface using our cell. So in other words, the surface geometry is not approximated at all. In other words, if you basically calculate the volume using this particular grid, and if you calculate the volume using a grid that is 5 times finer, the volume is going to be exactly the same. This is one of the nice features of Converge because you are not losing geometric details when you're coarsening the mesh. All right, so here what we can think about doing is, whenever you have a pipe, it's good to have at least a few cells across a diameter. So here we have 2, 3, 4, and then there is a cell here which is cut in approximately half, right? So this leads to something called as a cell pair. We are not going to be talking about cell pairs right now, but you can think of that as a separate cell for now. Okay, though it's not, just assume that it's a separate cell. So we have 1, 2, 3, 4, and 5 cells, which is okay. It's a decent start. It can be better, but the main problem is this guy. So here what we need to do is we need to make sure that we have more cells. And to do that, what we can do is we can use a technique called as a fixed embedding. So how does that work? So I'm just going to go back to my geometry, go to my case setup, all right, and click on grid control and then activate fixed embedding. Okay, so let's put the geometry where we can see it, and then let's click on fixed embedding, and then we are going to add a new embedding. So embedding refers to local mesh refinement, and the type of embedding that we are going to do is a boundary embedding. Okay, so we are going to select our throttle boundary, and then we are going to add an embed of scale 1, and the number of embed layers I'm going to set it to as 2. Okay, and with respect to the mode, we are going to keep it as permanent. So what does the scale parameter mean? So Converge uses an octree data structure approach to create the mesh. So the grid is represented in multiples of 2. So if your base grid size is 4 millimeters, what we are saying is near the throttle valve, the mesh size is going to be 2 millimeters. And we are using boundary embedding. So we know how the boundary is shaped. So on top of the boundary, we refine the mesh automatically. So what I can do now is, maybe instead of using a scale of 1, I can use a scale of 2, click OK, and then I'm going to export all of my input files. So, okay, so I'm going to create a new folder, and let us just call this as steady state. And I'm just going to say with embedding. Okay, we have selected this folder, and let's just export all of our input files. And we are going to follow the same process. So let's open Cygwin. And then we are going to go to steady state with embedding. And then we are going to run Converge. You can see that it's running. And you can see that if I look at the cell count, it is slightly more. So now we can go back to the embedding and maybe increasing the embedding level to maybe a scale of 3. And maybe I'm going to add 2 layers and export it in the same folder. So I'm overwriting. And if I execute Converge again, this time it's a bit slow as expected, and our cell count should be a little bit more. So you can see that we have now 100,000 cells. So the next thing we need to do is post-process this guy. Now you can see that only one file appears, and I'm going to convert all the data. Okay, the process is done. So now we can launch ParaView. All right, so now I'm going to open up the file, Converge runs, elbow flow, output, test.ca case. So notice that this time, we post-processed using Insight format, which should be fine. So if I click on apply, I'm getting an error. Okay, so it seems like Converge customized Insight format is not supported in ParaView. So I'm going to click on regular Insight, or you can just do ParaView. I just wanted to demonstrate that you can read Insight files in ParaView. All right, so that's done. And so now here I can delete the existing files and then reload the case file, and this time it's going to read. All right, perfect. So now you can see that I see the geometry, and the multi-block inspector is here. And what we can do is we can do the same thing. So first what I want to do is make the elbow wall a bit transparent. All right, so now I can see my throttle, and I'm going to create a clip plane, and we have to do a Z normal and then click apply. And then we are going to look at the surface with edges, and then we have to click on triangulate the slice, apply, maybe hide the plane, and we are just going to color the slice by a solid color so that we can see the mesh. And now if I zoom in, you can see that here I have at least 2 cells, and here maybe not, I don't have a lot of cells, but that's fine. We can continue this process and maybe refine this a little bit more, The other way I would go about doing this problem is, make the base mesh smaller. So what we can actually do is go back to our case and make the base mesh 2 mm. This is going to increase the cell count a lot, okay? And for base and for the embedding, we still have the same parameter. Export all input files. And then let's try running Converge again. So before I do that, I'm just going to open up ParaView and delete all of my data. Go to the output folder and make sure that we clean all the files. And then we can run Converge. So this time it is going to take a little bit of time, and our cell count is now 300,000, right? Actually 400,000. So we can go back to Converge Studio for post-processing. Doing that, you can see that the mesh distribution is a little bit better. So one thing we want to make sure is that, we don't have a local embedding at a very high level and the base mesh at a very low level. It's fine if you're doing that for a short duration of time. So in this case, I'm okay with this distribution and the cell count is not that bad. So let's just go with this. All right. So now what I'm going to do is I'm going to run the simulation in parallel, and then I'm going to check the results after every 1000 cycles, right? Before we do that, you just need to make sure that you are writing outputs frequently. So if you open your input files, and if you search for twrite post, that is the interval at which your post files are written, okay? Now you can see that your output files, your ASCII output files, where you have data like mass flow rate and the pressure inside the domain and the volume of the domain, those files are updated every cycle, so which is good. So what we are going to do is we are going to close this file and we are going to run the simulation in parallel. So I'm going to use MPI-EXEC -N4 Converge, and what I'm going to do is I'm going to take the screen output and I'm going to pipe it to a log file. So this way we can keep track of the simulation, because oftentimes if a simulation crashes, important information about the simulation is provided in the log file. So we need to check it, make sure that it looks good. All right, so let's run the simulation. And one nice thing about using Cygwin is that it provides a lot of command line tools. So what I can do is I can just type in tail log file to check the last line. So you can see that the simulation has run around 84 cycles. And if I do that again, it gets updated. You can also do a live update. You can say tail -f log file, and that's going to keep on dumping screen output. So we don't want that. All right, so currently we are at cycle number 223, and this is going to take some time. Alternatively, what you can also do is in Converge Studio, go to the line plotting, and then we are going to go to our steady state with embedding path, and I'm going to make a plot of mass flow rate in boundary number 3. All right, so if you don't know what boundary number 3 is, you can just go to your case setup, go to view folder. So boundary number 3 is your inlet. All right, so the inlet, the mass flow rate is still evolving. It has not reached a steady state value. So I'm going to create a new plot for this. You can give your plot any name you want. You can configure that. Okay, so for example here, I can just call this as inlet mass flow. All right, so the other thing I can do is I can go to my plot settings and go to auto update, and we can say that every 15 seconds we want to update the plot. So we can click OK, and if I click on this guy right here, it's going to start updating the plot. But before I do that, let's make a couple more plots here. I want another plot that shows the mass flow rate through the outflow boundary. We are just going to rename the label outflow mass flow. All right, so in addition to this, you can create more plots as required. So let's just tile the plots. So now that we have the tile, what we can actually do is we can minimize the preview plot. You can see that there's a title called preview. And then we can click on this first plot and then hit this play button. So when you do that, the plot gets updated automatically. And you can see that there is this flashing refresh sign, which means that the plot is getting updated whenever data is available, and it's trying to update it every 15 seconds. So you can see that we just saw an update there, and you can just let this sit for a while and then make sure that your simulation runs smoothly. So in your case, if you're running this job on a laptop, it's going to take a few hours to complete. So you can periodically check this plot to make sure that your simulation is taking place correctly and you don't have any weird oscillations in your solution. So we have already completed 1000 cycles, so it might not be a bad time to actually look at some output data. So what I'm going to do is go back to 3D post-processing, and this time I have a couple of files. So let's just select all the files and then call it test, and then just convert it. All right, so the process is done. We can launch ParaView, delete our files and go to recent files, and then since the name of the case file is test, since it hasn't changed, I can just reload it. And when I click apply, you can see that there are two data points. There's time 0 and time number 1. So go to the multi-block inspector, hide convert cell data, and we are going to be doing the same post-processing. So practice this a couple of times. I know that we are repeating steps here, but that actually helps you understand like the workflow, and you won't forget it. Oops, I actually changed the opacity for the wrong boundary. So let me click on elbow wall and make it transparent and hide the convert cell data because that's in your way. And we're going to create again a Z normal plane. Click apply. Okay, you can see that I've actually done a clip. I actually wanted to do a slice. So let me delete it and then do a slice, Z normal, and just click apply. Perfect, this is what I want. And we also want to make sure that we uncheck the triangulate the slice option, click apply, put the geometry like this, and we are ready to look at some results. Hopefully we have some results. So let's look at the second data point, and we're going to look at velocity. And you can see that slowly you start seeing some velocity information, and the peak velocity is quite high. So let's hide the plane and look at this in closer detail. All right, with respect to the color map, I'm really not a fan of this default color map. So let's basically use the default one, blue to red rainbow. Then you can actually see how the velocity looks like. The velocity field is still developing, obviously, so it's going to take some time for the flow field to develop. In the meantime, you can look at some vector plots, and we are going to be looking at velocity vectors, and make sure that you start with a lower number of samples, especially if you're trying to post-process when your simulation is running. You might be running out of memory, so maybe start with 100 points. So this actually tells you how the flow is taking place, and you can play with the scaling factor to make the plots a little bit better, but that's not the whole idea. The idea is not to make pretty plots. We want to make sure that the flow takes place in the right direction, because sometimes you set up the inflow and outflow boundary conditions oppositely, and hence the flow is going from outflow to inflow. So you need to make sure that those things happen correctly. All right, what else do I want to do here? So I can go back here and just hide everything except the throttle, and we can make sure that the throttle is perfectly opaque, and we can enable it. So then you will be able to see the throttle as well, right? And what we can do is we can now color the throttle if we want to. So in this case, I can color the throttle by, say, the pressure, right? And we're going to use a custom color map for the pressure as well. And we're going to be using our blue to red rainbow color. So here you can see that when the flow encounters the throttle, the pressure is a bit higher, right? That is understandable. And then behind you have low pressure regions, because that's where the flow is going to separate, and the low pressure indicates a drop in static pressure. All right, so I can actually hide the glyph so that we can just look at, maybe even hide the slice so that we can look at the throttle. And you can see that rotating it is a bit hard. That's because the center of rotation is somewhere else. So I can click on this guy right here and then place the center right here, and I should be able to rotate it more comfortably. So you can see how the flow structures are taking place. There is some flow through the side, and that's expected because the throttle is not perfectly sealing the channel, right? You can have flow from top, left, bottom, and right, because this is a made-up geometry. Okay, but it seems like the results are a bit physical. Nothing unphysical is happening so far, so we are good to go. So I'm just going to wait for a little bit longer, maybe check on our plots to see how it looks like. You can see that my mass flow rate is slowly starting to reach a steady state value. We can just wait a little bit longer, and maybe roughly at 6,000 or maybe even 7,000 cycles, we can just stop the simulation and we can look at the results. Okay, all right, so looks like the simulation is complete, and you can see that the inflow and outflow mass flow rates have converged to a particular value. And similarly, what you can also do is you can look at other flow quantities. In this particular case, there's not a lot of interesting things going on. So what we can do is open up Sigwin and do ls, and then if you do a tail of your log file, you will see that the total simulation time is printed out. Okay, and in fact you can do tail -100, so that's going to print the last 100 lines. You can see that it took about 2015 seconds, and here is how the time was split. So solving the transport equations, right? So in this case you're solving your momentum equations, and then you're having your k and epsilon equations since you're solving turbulence. That's about 1565 seconds, so that's 77% of your runtime. Move surface and update grid, it's about 0.63%. So in this case there's no moving parts, but still the grid is generated every time step because that's how Converge does it. Now in steady state simulation, when there is no AMR, it optimizes some of the things, but it still takes a little bit of time. All right, then writing output files is the next major thing. In this case, we are writing post files and also writing to ASCII files. That's taking the most amount of time. What else can you do? So you can see that there are a lot of files written out, and each of these files contain outputs, and the names are quite intuitive. So for example, thermo.out contains the thermodynamic properties, and this is a volume averaged data. So if I open thermo.out, here you can actually see that for each iteration, what's the volume averaged pressure, what's the maximum pressure in the domain, minimum pressure in the domain, what's the mean temperature, max temperature, and min temperature, and so on. So the thermo file contains thermodynamic properties. Similarly, if you want to look at other things, so for example, we already looked at mass average flow.out. Now if we want to look at turbulence quantities, there is a file called turbulence.out, and if I unwrap it, you can see here it contains the turbulent kinetic energy, turbulent dissipation values, again averaged for the entire domain. Now we still haven't talked about turbulence modeling, so most of these parameters is going to be a bit mysterious for you. But the whole idea that I want to convey is in these output files you have meaningful data which you can look at, which you can plot, and you can get engineering quantities out of it. So this concludes the case setup for the steady state simulation. So now what we are going to do is we are going to set up the same problem using a transient solver. And what I'm going to do is I'm going to go back to my old setup, and here let's actually maybe hide this guy. And what I want to do is I want to rotate this throttle. Okay, and couple of things which we need to think about is as we rotate. Okay, so the transparency tool here is not that good. Maybe I'll just go here and I can show it. So let me enable the elbow wall. There we go, perfect. So, you know, as we rotate the throttle, we need to make sure that the throttle surface does not intersect with any of the parts, you know, because then that would actually cause an invalid surface, and that's not what we want. All right, so in this case, you can see that the rotation axis is basically the axis of the cylinder that we drew in SolidWorks. So what I'm going to do is go back here and redisplay everything, maybe set the transparency back, case setup, and we're going to start all over again. So we are still going to be doing the general flow application. All right, so this time in simulation parameters, you know, there's nothing different. We still have the same things. Now in run parameters, the first thing we are going to do differently is we are going to use a transient solver. Now, why are we using a transient solver? Because the throttle body is actually moving, and this is a transient problem. So for example, whenever the pressure changes, whenever there are oscillations, we want to make sure that we capture that transient behavior. Again, if that is the aim of the simulation, then you know, that's why we are simulating the moving part, right? Else we won't do it. So since we are simulating the moving part, we need to do a transient simulation to capture those dynamic effects. Okay, so let's click OK here, and that's going to load a different set of constants. We just use the default values for now. And now you can see that this time the start time and end time is in seconds. So one way to think about the end time is by using something called as a flow through time. So here, if I enable the bounding box, you can see that, you know, the characteristic dimension is roughly 0.1. So ideally you want to calculate the length of this pipe. So we can just say that, you know, it's going to be maybe maximum of 0.2, you know. And then what we can do is we can actually look at the velocity. So if I go to the plot and if I look at the velocity, you can see that the average velocity through the inlet is 80 meters per second. So the characteristic length is 0.2 meters and the velocity is 80 meters per second. So that's your flow through time. So that's how long it takes for the flow to go through that pipe once. So let us say in this case we want to simulate maybe 3 times that or 4 times that. So 2 milliseconds, maybe we want to simulate it up to 8 milliseconds or maybe 10 milliseconds. Okay, so that would be a good end time. So let us go with maybe 10 milliseconds in this case. So 10 milliseconds is 0.01. I believe that's correct. And the initial time step, I'm going to start with 1e minus 9, minimum time step 1e minus 9, and maximum time step of 1 second. So nothing changes there. So the main thing which we are going to do differently is this guy. We want to make sure that we rotate the throttle plate and we have to set it up correctly. So we go to boundary and we select our throttle body and we say that it's a wall type, but the wall is actually a rotating wall, right? So which means it requires a rotation center and an axis of rotation, right? So what I'm going to do is maybe I can just hide this guy and also that guy and that guy, right? So you can see that you have the cylinder. Now the cylinder, there's a circle on the top. Again, it's not complete, but you can imagine that. The center of that circle is what we want to give as the rotation center. And then what we want to measure is how this valve is inclined, right? That will actually help us figure out how to go about the rotation axis. So to do that, Converge provides a lot of cool things. So since we are trying to measure the center and the normal direction, you know, if I click on measure and then if I go to direction, arc normal, what I can do is I can select a couple of points. Actually, I need 3 points to measure the arc normal. So if I click on apply, you know, I'm going to get an arc center and an arc normal. So what we can do is we can just copy this arc center, right? And inside boundary for the throttle, I can say that that's my rotation center. So what about the axis? Well, you have the arc normal, right? So that's going to be the direction in which, or that's going to be the rotation axis. So if you're not comfortable with this guy, rotation axis, you can think of it like this. So you can see that when I display the normals, you can see this arrow, right? And if I put the geometry in maybe this view, so this direction indicates the axis about which my throttle plate should rotate. Okay, I hope that makes sense to you. And to calculate that, we are measuring this arc normal. So we are using 3 points. So with 3 points, you can compute 2 vectors. And with those 2 vectors, you can actually do a cross product to determine the normal. Alternatively, what you can do is you can go to measure, you can do triangle normal. And if you just measure this normal, maybe just pick one guy. I'm going to clear all and then just pick one guy. And if you click apply, you can see that I get pretty much the same answer. All right. So here in this case, I have 0 for the Z component, but that's fine. It's pretty much the same. 3.6 E minus 5 is as good as 0. This one might be a bit more accurate because we are measuring it on the triangle itself. So let's just copy that. And for rotation about, we just paste that vector. Okay, so the next thing we need to do is we need to give a rotation rate. So we can continuously give a rotation rate. So that means what's going to happen is the valve is going to keep on spinning. Well, we don't want that. What we want is we want the valve to basically maybe rotate by 20 or 30 degrees and then stop. Okay, so we can actually see how the flow looks like. So what I'm going to do is for the rotation rate, I'm going to use a file. All right. And here, what I'm going to do is I'm going to say at 0 seconds, the angle is 0. And maybe roughly in 2 milliseconds, the angle is 25 degrees. So for the remaining time of the simulation, the angle is going to be 25 degrees, right? And we can just give it a name, throttle position dot in. Remember, it's a good practice to provide dot in as an extension. And that's basically it. So we click on validate and that solves the problem. So we now need to go to output and post processing. And for output files, now we want to write outputs maybe every time step. So 1E minus 6. What about time interval for writing 3D output? Well, this you can actually make an educated guess. So for example, in this case, we are running the simulation for 0.01 seconds. So let us say you need 10 output files. Okay, so if you need 10 output files, then this interval is automatically going to be 0.001. All right, so let's click OK, and we are going to export everything. So export all input files, and what we can do is elbow, and then we can create steady state transient. All right. So all of my files have been exported. So whenever you set up a transient case and that involves a moving boundary, it's a very good idea to actually make sure that the mesh generation process takes place correctly. And to do that, what you can do is in run parameters, there is a simulation mode called as no hydrodynamic solver. This is not going to do the CFD part. It's going to just create the mesh for each and every time step. So this process is relatively fast. So I can either select no hydrodynamic solver here and export all of my input files, or I can open up my command window, open up inputs.in. Oops, before that I need to make sure that I'm in the right path. Steady state, transient. And then we are going to say no hydro is equal to 1. All right, and we can run this in serial first to make sure that it runs through. You can see that this runs fairly quickly. We can run this in parallel. And then we can continuously monitor the log file to make sure that the simulation is progressing correctly. So here you can see that this is our total time, and this right here is basically your time step. And since the throttle is actually moving, the cell count is actually a bit different, because depending upon the position of the throttle, the cell Cartesian method is going to generate slightly different number of cells, and that is why you can see that the cell count is different. All right, the simulation is complete. It took only 46 seconds, which is not bad. So if I go to the output folder, you can see that I have 10 post files. So let's go back to Converge Studio, go to the output tab, and then this time what we're going to do is set up the transient flow, and we're going to post process all of it and then give it a file name test. All right, so that process is complete. I can just delete all of my current variables in ParaView, and then click on open, navigate to the right folder, output, and then open test.case. In 2 milliseconds it reaches that particular value and then it stays there. And if you make the mesh, and then if you select your slice and then just display the mesh, and then just click on triangulate the slice or uncheck it, you can see how your mesh is getting created. So this is the beauty of cut cell Cartesian method. The mesh generation process is quite easy, and you can see that the mesh automatically moves, and when the mesh moves, the embedding also moves. So now what we can do is we can set up the flow simulation. So I can just go back to Sigwin, navigate to the right folder, and then we go to no hydro, and then we set it to 0. All right, so then what we are going to do is run the case in parallel. Impia exec minus n4 converge, and then pipe it to dev null log file. We already have a log file that is going to get overwritten. So if I hit enter, oh sorry, before I do that I need to put the ampersand sign so that the job runs in the background. Okay, so the job has been submitted. So if I do tail log file, you can see that the simulation is going on. And you can use the grep tool to grep for dt in log file to see what your time step is. So time step is growing, and this is your current simulation time. So we are going to wait for the simulation to complete, and then we are going to look at the output data. All right, so I've loaded the files, and now you can actually see how the flow structure evolves. So if I go to the first time step and if I play the simulation, you can see how the flow interacts with this throttle and then finally reaches a steady state. We don't have a lot of time steps, so it's very hard to see the difference. So let's just try to go one time step at a time. So this is after 1 millisecond. And then now you can see that when the throttle moves, it's closing the area a little bit more, and then that's going to cause more density variation. So we are looking at density here. So if we look at velocity in the same plot, and then if I use a different color map here, and then we just need to make sure that we rescale the velocity. All right, so if I go back one more time step, you can see that that's how the velocity looks like. And if I go one more time step, now you can see that there is larger regions where velocity is becoming 0. That's because when the valve closes, it's going to create more recirculating zones. If I just keep doing that, you can see that then the flow pattern just keeps on changing, but it reaches a steady state value, right? And 5, 6, 7 milliseconds, you can see that the flow pattern is changing, but it's not changing a lot. All right, so we can set up this case slightly more fine so that you can see the flow oscillations a little bit more, but we don't have to do that for now. All right, so the next thing that I want to show you is how to create a streamline. So the idea behind streamlines is to visualize how the flow takes place, and to understand that, let me give you an example. Imagine that there is a river and you put some paper particles in the river, and if you keep on taking pictures of that paper particle, several times a second, and if you put all those pictures together, you can actually track how the paper moves, right? So that is a path line, right? So here what we can do is, at each and every time step, we have a velocity field. We can use that velocity field and we can introduce some particles, and we can see that how those particles move if that is the velocity field, right? So the velocity field changes with every time step, so the flow structures are also going to change, right? This actually helps us to visualize how complex the flow path is. And to do that, what I'm going to do is select test.case and then use the stream tracer. The thing I need to do is I need to set up a location where I introduce all of my particles. This is called as the seed point. And here what we are going to do is we are first going to choose our seed, which in this case is going to be a spherical source. So we use a point source and immediately a sphere appears. So what we are going to do is we are going to introduce a bunch of particles inside the sphere, and if the sphere is inside the pipe, then those particles are going to be introduced in the pipe and then it's going to flow. So to do this, I'm going to first put my geometry in a proper view, and then I can just move the sphere to the required location, and just check a couple of views to make sure that the geometry is inside, and you can just move it around to see that you are in the right location. So we are going to start by introducing 100 points inside the sphere. So let's just click apply, and you can see that the calculation is done, but you don't see anything. That's because we are in time step number 0, which is the initial conditions where there is no flow field. So if I go to the next time step, hopefully you will see the streamlines. Okay, and when I change my background to black, you can see that the streamlines are quite visible. So now that we are able to see it, we can increase the number of points to say 200. This is going to take a little bit more time, but now you see all your lines. It's quite dense, which is nice. The next thing that I'm going to do is adjust the transparency so that I can see the streamlines a little bit more clearly, right? And we can also color it by the velocity. Okay, so this way you know where the high velocity is and where the low velocity is. And I'm going to change my color map to something like this so that it looks much more visible. You can enable test.case so that you can see all of it together, and if you want, you can completely hide the elbow, or you can make it really transparent. Something like that. And what else can we do here? Well, if I go to my stream tracer, go to properties, I can just uncheck show sphere so that I don't see it. Then you have all sorts of control. For example, there's a parameter called line width. I can just change that to increase the line width. You can play with those things if you want to. Alright, so now we are going to take a closer look at the model, and then I'm going to change the center of rotation so that I can control the model quite easily. So something like this. And then if I go to the next time frame, now you can see that the flow structures have changed, and this is what happens. So the flow is really chaotic when there is a throttle valve, and that's going to cause a lot of oscillations. It's going to cause high pressure and low pressure zones near the throttle vicinity. And we are able to predict these type of things with Converge quite comfortably. So that concludes this particular lesson. I have provided the geometry for you. Like I said, the geometry has been oriented slightly differently, and you will be using a different profile for the throttle, and you will be working on a small project. Okay, all right. If you have any questions, get in touch with me. Good luck. Bye.